This is section 5.3, the fundamental theorem of calculus. Our second objective is to understand and apply part 2 of the fundamental theorem of calculus. When we're done, I'd like you to be able to write part 2 of the fundamental theorem of calculus in your own words. So first, let's recall part 1. Part 1 of the fundamental theorem of calculus says if f is continuous at every point on the closed interval from a to b, then an antiderivative of little f has to exist. Now we're going to switch the letters up just a little bit, and we're going to say that antiderivative now is capital G. Capital G will equal the definite integral from a to x on little f of t with respect to t. And this antiderivative will exist, and it will have a derivative at every point. So that means if I take the derivative of g, I'm going to get the derivative of that integral, and part 1 will just dump that x inside and we'll end up with f of x. So this is an antiderivative because when we take the derivative we get f of x back. So let's recall too that if capital F is any antiderivative of f, then it's going to differ from g of x by a constant. Why? Well, because all antiderivatives of a given function can only differ from each other by a constant. So what? We already knew that. How does that help us? Well, let's look at the difference between two interesting outputs on f. We want f of b minus f of a, and we'll remember that that's the same thing as g of b plus c minus g of a plus c. If I distribute my negative, we'll see that the c's cancel, and the difference between g of b and g of a is going to be the same as the difference between f of b and f of a. Well, there's nothing too earth-shattering here yet, but what happens if we rewrite g using the integral notation instead? Let's remember that g of b minus g of a is going to be the output of that weird antiderivative with the b plugged in. So that was the integral from a to b of little f of t with respect to t minus the accumulation from a up to a on f of t with respect to t. And that is also going to equal capital F of b minus capital F of a, because those were the same thing, which is what we showed on the previous page. So now let's think about this piece right here. We know if we accumulate from a to a, we get nothing. So that means this g of b minus g of a is going to be the same as f of b minus f of a, which in turn will be the same as this definite integral. So the definite integral of little f from a to b can be computed as capital F of b minus capital F of a, where capital F is any antiderivative of little f. You may be shrugging at this, asking, what's the big deal? But what you should be doing is shaking your head in amazement. Why? Because this means that if we know even one antiderivative of the integrand, in other words, if we can answer the question, what did I take the derivative of that gave me this little f? Then the definite integral of any continuous function can be computed without Riemann sums, without limits, and without a lot of mathematical gyrations and heartache. All you have to do to find the definite integral is to find the difference between the antiderivative evaluated at the upper limit and the antiderivative evaluated at the lower limit. Don't believe me? Let's look at an easy example that involves geometric shape. Let's say we want to compute the definite integral from -4 to 6 of the function 2t with respect to t. We can do this the old way using geometry. We graph the integrand, which is y equals 2t, and then we accumulate from -4 to 6. Down here on the bottom we have a triangle, and up here we have another triangle. And remember that the accumulation will be the area above the x-axis minus the area below the x-axis. So the area above will be 1/2 6 times 12, whereas the area below will be 1/2 4 times 8. Put that all together, we end up with a definite integral that equals 20. So now let's use the fundamental theorem of calculus part 2 to do this same problem. If instead of graphing, we want to simply answer the question, what did I take the derivative of with respect to t that gave me 2t, then the answer to that would be a t squared plus any constant. Now, because the fundamental theorem of calculus part 2 says we can use any antiderivative we want, we can make it easier on ourselves by just allowing that constant to be 0. So what we need to do now, this is our antiderivative. We are going to evaluate it at the upper limit minus the evaluation at the lower limit, and we'll get 36 minus 16, and what do you know? We get that same 20 that we had before. Now you may argue that this method too wasn't much easier with this example, but it is much easier when the integrand's accumulation cannot be represented using nice geometric shapes. So let's try a couple of those. If we look at example 2, you can see that I have represented each of these definite integrals graphically so that you can kind of see that none of these are nice geometric shapes. So our old methodology would require us to do a Riemann sum, which could be very time consuming, especially if we wanted that approximation to be really close. So instead, we're going to use part 2 of the fundamental theorem of calculus, and that will require us to answer the question, what did I take the derivative of with respect to x that gave me the inside function? Hopefully, because we did section 410, you're able to go backwards. The antiderivative of sine of x is a negative cosine of x, and we will evaluate that first at the upper limit, and then we will subtract what we get when we evaluate it at the lower limit. So if we think about our unit circle, cosine of pi, that's the x-coordinate on the unit circle, at pi radians, which is -1. So this is the opposite of a -1. Then we're going to subtract the opposite of cosine of negative pi, which means we go around the other direction to the x-coordinate, and we still get a -1. If I simplify all of that, we end up with 0. And we can see that graphically because the accumulation underneath the x-axis is the same as the accumulation above, so they will essentially cancel one another out. If we look at part B now, we want to accumulate from 0 to 2, and we need to answer the question, what did I take the derivative of with respect to x that gave me this inside? Hopefully you can answer that that will be an x cubed plus an x squared minus a 5x. Again, we will evaluate at 2 first, and then we will subtract whatever comes out when we plug in the 0. Put those together, we have 12 minus 10, and we get a 2. Next, what did we take the derivative of with respect to x that gave us 1 over x? Hopefully you remember that that's the log natural of x, evaluated from 1 to e. We plug the e in first, and then we plug in the 1, and subtract that output. So we'll end up with a 1 minus a 0, which is 1. So what's interesting is this accumulated area is exactly 1. If we did an infinite number of rectangles and added up their areas, we would get 1 exactly. With part D, we need to answer the question, what did I take the derivative of with respect to x that gave me this inside? Now notice that this is one of those derivatives you should have memorized. So hopefully you'll remember that that is the tangent inverse of x, and we're evaluating from -1 to 1. So this asks first that I put in a 1, and then I subtract what comes out when I put in a -1. Well, to figure out what this equals without a calculator, I need to know what I took the tangent of that gave me a 1. Hopefully you know that that's a pi over 4. And then I will subtract the angle that I took the tangent of to get a -1, which is a negative pi over 4. Put those together, we end up with a pi over 2. So this area is exactly equal to pi over 2. Now once we get good at computing definite integrals, there are lots of applications involving definite integrals that we can do now as well. We'll do a couple of basic ones here, and then we'll ramp it up with story problems in section 5.4. With example 3, we want to find areas between functions and the x-axis on a given interval, both with and without a calculator. So if we look at part A, we can see that we have a piecewise function. One branch of it is the square root of x, and the other branch is an x squared. And I want to find the area between the curve and the x-axis from 0 to 2. So to get that area, we know that because the entire graph is above the x-axis, the area will equal the definite integral. Now, writing the definite integral this way, we can't really answer the question, what did I take the derivative of with respect to x that gave me f, because f has two different branches. So what we'll need to do is we'll need to split it among its pieces. So we'll accumulate from 0 to 1 on this square root of x, and then we will continue on from 1 to 2 on the next branch. Now we're set up to answer the questions posed by this integral symbol. What did I take the derivative of with respect to x that gave me x to the 1/2? Well, we're going to add 1 to the exponent and divide by the new power and evaluate that from 0 to 1. And then we will add the answer to this one. What did I take the derivative of with respect to x that gave me x squared? Well, that's an x cubed over 3, and I'll evaluate that one from 1 to 2. If I plug in my 1 here, I'm going to get 1 to the 3/2, which is 1, divided by 3/2 is the same as multiplying by 2/3. And then I'm going to subtract what comes out when I plug in the 0. For the next piece, I'll plug in the 2 first, and then I subtract what comes out when I plug in the 1. Put that all together, I have 2/3 plus 8/3 minus 1/3 gives me 9/3 or 3. With part B now, it's a little different than part A because the entire function is not always above the x-axis. That means that the area is not going to be the same thing as the definite integral. So we could say that the area is the same as the definite integral from 0 to 2 pi on the absolute value of that cosine of x. And if we have a calculator, we could just plug that in and get the answer. But I want to be able to do this without the calculator. So to do that, I'm going to use what I know about the symmetry of cosine curves and about the periodicity. I know that this accumulation here is the same as this accumulation because the y coordinates are the same as we go through the cyclical versions of cosine. Same thing underneath here. We know that this accumulation is just the opposite of whatever was above. So I can rewrite this as 4 accumulations from 0 to this location on the cosine graph. So to figure out that location, I need to think about when cosine equals 0, and cosine equals 0 at pi over 2. Now that I have this written up, I can say 4 times whatever I took the derivative of to get cosine, and that would be a sine of x evaluated from 0 to pi over 2. Plug in pi over 2 first, and you get 1, and then subtract what you get when you plug in 0. Multiply that all out, and I end up with exactly an area of 4. With part C now, we have the same concern that we had on part B. We can't just simply integrate from -2 to 2 because part of this integrand dips below the x-axis. So if I'm interested in finding the area will be the accumulation from -2 to -1 of that 3x squared minus 3 with respect to x. That accumulation will be positive, so it will equal the green area here on the left. And then I'll have to add the opposite of the accumulation from -1 to 1. The reason I add the opposite is because the accumulation is a negative number. In this red region, I'll accumulate negative values. So to make it into an area, I need to take its opposite. And then I will again just compute the regular integral from 1 to 2 on that 3x squared minus 3 because again I need to compute the accumulation, which is the same as the area for this green region. So I could individually compute each of these definite integrals and get the answer. But if I want to do this by hand, I want to look for shortcuts. I want to look for ways that I can minimize my labor. So to do that, I notice first that these two green regions are the same. And I would rather work with positive numbers than with negatives. So I'm going to replace these two with 2 of the 1 to 2's. And then I'm also going to see on this red region that I have some symmetry. If I slice it right in the middle and then double it, that's going to give me the same thing as if I go from -1 to 1. And I would rather work with a 0 than with a -1. I'll tend to make fewer errors. So I'm going to now add the opposite of 2 of those 0 to 1s. Now that I've minimized the number of integrals I'm going to have to take, in addition to making the limits nice numbers, I'm ready to answer the question posed by the symbol using the Fundamental Theorem of Calculus Part 2. I will have 2 times the answer to the question, what did I take the derivative of with respect to x that gave me this integrand? And the answer would be an x cubed minus a 3x. And I will evaluate that from 1 to 2. Then I will add the opposite of 2 times the answer to the question, what did I take the derivative of with respect to x that gave me 3x squared minus 3? Well, that's the same answer I got before. I just have different limits from 0 to 1. So if I put this limit in here, 2, I'll have 2 on the outside times an 8 minus a 6, and then I'm going to subtract what I get when I plug in a 1, which is a 1 minus a 3. Then I'll add the opposite of 2 times what comes out when I plug in a 1 minus what comes out when I plug in a 0. If I simplify this all up, I get 2 minus a -2. That's 4 times 2 gives me 8. And then I have a -2 times a -2 gives me a 4. And I end up with 12. Now, because I told you you could use calculators or not, I also want to think about how, if we had a calculator available, we could have done this very quickly on the calculator. We could simply accumulate from -2 to 2 on the absolute value of that function, because when I take the absolute value of it, it pops the red portion up, and now if I accumulate straight across, the green accumulation will be the same as the original area. So if I put this into my calculator, you can see that we'll do second 7 to access the integral. We'll go to our catalog and scroll to the a's if we aren't already there. Absolute value of 3x squared minus 3. Close the absolute value. Tell the calculator we want to integrate with respect to x. Tell the calculator my lower limit, and tell the calculator our upper limit. Hit diamond enter. We should end up with the same value we got doing it by hand. And we do. For part D now, we want to find the area in the first quadrant enclosed by the coordinate axes and the graph. So we can see right away that the definite integral to whatever that limit is, we don't know what it is yet, but the definite integral is going to be the same as the area because it's above the x-axis the whole time. So in order to find that area, we need to write this as a function. To do that, we will need to isolate our y. So if I do that, I'll get a cube root of 1 minus an x cubed. So the area in the first quadrant will be the accumulation from 0 until, if I think about when the y value is 0, set this equal to 0, or set this equal to 0, I can see that x is going to be 1. So I'm going to intersect here at 1, and I want to accumulate from 0 to 1 on that cube root function. Now, we do not have the skills yet to answer the question, what did I take the derivative of with respect to x that gave me this? So we will have to do this one on our calculator. So enter second 7, and to enter in the cube root, you need to do 1 minus x cubed raised to the 1/3 power. We're integrating with respect to x from 0 to 1. Hit diamond enter, and we get 0.883. With our fourth and final example, we want to compute differences between two integrals. And if we look at this example, we want to find k. We want to find what we add to this accumulation in order to get the accumulation from 2 to a. So we're going to approach this two ways. The first is to do it analytically and to isolate the k. If we isolate the k, we'll have the accumulation from 2 to a on sine squared of x with respect to x, and then we will subtract the accumulation from 0 to a of sine squared of x with respect to x. Now looking here, I don't know what A is, so in some way I need to rearrange the way this is written so that the A disappears. To do that, we will use our additivity property, which says if the top limit on one matches the bottom limit on another, then they can cancel out and be combined into a single integral. So what I'm going to do is I'm going to switch this one, which will change the sign. So I'll go from 2 to A on sine squared of x with respect to x, and then I will add the A to 0. When I do that now, hopefully you can see that that is the same as accumulating from 2 to 0, which is now something I can put into my calculator. So get your calculators out, and on the home screen, we're going to do the second integral, second 7, of sine squared. So that means I've got to put the sign in first, and then square it, and then tell the calculator I want to integrate with respect to x from 2 to 0. Hit diamond enter, and we get negative 1.189. Now I want to think about this graphically and see if we can kind of come up with this on our own without having to remember the additivity property. This says I started with the accumulation from 0 to some value a on this function sine squared of x. And then I want to add a number so that I end up going from 2 to a. So in order to get just this portion, when I'm starting with the entire thing, I'm going to have to subtract the accumulation from 0 to 2. And notice that if k is the number that I subtract, that's going to be the opposite of the accumulation from 0 to 2. Notice that if we plug this in, we'll get the exact same thing. Now that we've done all of these examples, I would like you to try and reiterate what that fundamental theorem of calculus part 2 really says. Put it in your own words.